I'm a PhD student at Corey, Gavin. This is some work that I've been working on with Gavin and Shimon, who's online from Italy at the moment. Please bear with me. It's been a little bit of a all over the place this week, so I'm just going to keep things pretty informal. Some of it towards the end is just going to be talking through some figures and things. But hopefully I can convince you that wavelets, and particularly the wavelet transform and the continuous wavelet transform, hold potential in quantum field theory for studying scale-dependent phenomena and as a renormalization tool. So, yes. No? Cool. So, motivation. We're motivated because, well, quantum field theory has a lot of scale-dependent stuff that we'd like to understand. Wavelets were introduced originally in the field of geology. We've heard about them once today already, and you'll hear about them again in Simon's talk coming after mine. It's discrete wavelet theory and continuous wavelet theory. I'll talk about both in a moment. Both of them have already shown a little bit of promise in different areas, and we wanted to know, in the case of the Casimir effect, which is just a really simple, fundamental quantum field theory type prediction or explanation, what happens when we apply a scale-dependent cutoff arising from a wavelet picture? What effect does the wavelet have? How can we tune that cutoff? How can we understand that cutoff using different types of wavelets, and how do those two things interact? So, I'm going to start by talking about discrete wavelet bases, because they're a little bit easier to get your head around if you're not familiar with how wavelets operate. A wavelet basis is, you can think of it a little bit like a halfway point between a position basis and a momentum basis. It's built up of basis functions that have some localization in momenta and some localization in position, as opposed to pure position or pure momenta. They're constructed, I mean, the reason why they're called wavelets is because when you draw them out, they look like a little wave. They'll some sort of squiggle, and then they taper off to zero at infinity or minus infinity. They're defined recursively, which is really interesting, in terms of a set of wavelet coefficients, like so. And in the discrete case, what we're interested in is taking integer translations of these basis functions and dyadic scalings, larger and smaller. And they're defined recursively, meaning they're defined in terms of themselves. So there's two pieces of the wavelet basis puzzle. You've got the scaling functions, which are defined in terms of themselves at smaller scales. And then you've got the wavelet function, which is defined in terms of the scaling functions at one finer scale with a flipping sign. So in that sense, the scaling functions operate like a low-pass filter, and they effectively sum whatever your signal is. And I mean, we talk about signals because it comes from signal processing. In our case, we're more interested in a field at a position space, I suppose, rather than a signal in time space, but they're more or less equivalent. Wavelet functions operate more like a high-pass filter, taking differences. A super simple example, by the way, of a wavelet transform, a discrete wavelet transform that follows this is the Hadamard transform, where you've got the two, you've got 1, 1, 1, minus 1. The top two rows essentially sum, and the bottom two is different. So by taking that rotation, you're taking a sum and a difference of two numbers. It's a bit like taking a low pass and a high pass. So this is going to be tricky if I have to keep doing page down instead of next. So to actually calculate these things, this is the same. This expression is the same for kind of all wavelets. The way you've got this set of wavelet coefficients. What you do is you assume some sort of desirable property, and then you solve for them. So in the case of Derived wavelets, you've got some number of moments that are zero, and you just assign that as an index. And then you solve for the smallest number of coefficients for which you can achieve a scaling function that has has that first number of moments equal to zero. So there's diagrams of 1, 2, 3, and 4. Derived wavelets. The Haar wavelet is the k equals 1 case, and so you've got the higher orders here, and they actually get smoother. And And you often, in the case of the discrete wavelets, get these really nice orthonormality properties that make some of the calculations quite a bit easier. You've also got this feature where you can break down, so working as a basis, I suppose, you can take any function in L squared on R, so L2 integral functions, and you can break it down into a sum of scaling functions at some resolution or some scale, and then the wavelet functions at that scale, and then successively finite wavelet functions. We can scale limit, we implement a scale limit in that discrete picture then by cutting off all of those wavelet functions that are finite at some particular scale. For the rest of the presentation, we refer to that as capital A. Cool. Now, continuous wavelets. In the continuous wavelet picture, what we do is we take the position and scale variables that were discrete. In the discrete picture, you've got the integer translations and dyadic scaling. In the continuous wavelet transform, both the scale and the translation parameters become continuous. That has a couple of implications. One of those implications is that there's no longer a scaling function, and you also don't have the concept of wavelet coefficients. What you have is you have this admissibility condition that I've put down here, whereby essentially it has to be finite. This particular integral has to be finite. And what you can do then is take any function in d dimensions, you can transform it like so, and the continuous wavelet transform essentially does this smearing, where it will take your wavelet, which functions as a kernel, convolves over all possible orientations, scales, and positions of that kernel, and then you end up with the wavelet transform. And as long as the wavelet satisfies the admissibility condition, that process is invertible. So that's sort of the illustration of what I'm talking about in terms of the action of the similitude group. Is just a fancy way of saying, yeah, we would talk about that to describe translations, rotations, and scalings. Here's an example of a 1D. Again, I pinched this from a geology publication where they just generated some sample data to explain how the continuous wavelet transform looks in one dimension. If you've got a simple pure sine wave in one dimension, you can see how the continuous wavelet transform has this idea of time, in our case position, but in their case time, and scale, and you can see how the features are both localized in momenta and position.
It's really just like musical notes, isn't it?
It is, yeah. Because exactly when you play a musical note, like a piano or whatever, it starts and it stops. It doesn't go on forever in both directions. So wavelets are perfect for that sort of thing. Nope. There we go. There's also, so there's the inverse transform. So this is, when as long as it meets the admissibility condition, that C sub W will be finite, and the invertible transformation can occur. There's this nice connection between wavelets and coherent states. I recommend you go and read and have a read into that if you're interested. Yeah, I don't understand that.
Me neither.
It also preserves inner product, and in the continuous case, we go from talking about a basis. In the case of the discrete wavelet transform, you've got this exact hologram. You need to do this exact mapping between before and after with quantum field theories. In the continuous case, it's a little bit more complicated. In some wavelets, we think you might be able to, if you put certain restrictions on, the scale and position, which effectively kind of discretize the continuous wavelet transform. In this case, we're just keeping it completely. We're not doing that. We're just talking about it in terms of the frame. In the continuous picture, we can scale limit the function by doing the forward continuous wavelet transform. And then when you do the reverse continuous wavelet transform, you're limiting the integration so that the scale is, instead of going from 0 to infinity, it's going from some smallest possible scale, capital A, to infinity instead. The inner product is transformed like so. And we have this addition of the function f called the cutoff function. And it's a bit hard to see what it's doing there, but in the Fourier image what you can see is that the f tilde is essentially a function of, I guess, that you're multiplying the frequency response by. So in a traditional band limit, momentum-based band limit, you've got this step function where you take all momentum up to some point and then cut it off. It's equivalent in the wavelet picture. It's equivalent to replacing that step function with something else, and that cutoff function will depend on whether the wavelet is. It might be smooth. It might taper off to infinity. It might go It might reduce smoothly and then go to zero, or it might not reach zero, depending on how you, depending on the properties of your wavelet. And yeah, sorry. So that's the inner product. That's the expression for f tilde, which is the cutoff function. Yeah. Now we looked at the Casimir effect because we were interested to see if it was a calculation that's well established. There's a set of technique. There's a regularization technique for that calculation that is quite straightforward, and we wanted to apply or see how you could do the use the continuous wavelet transform to do that regularization. Now, this has already been done in 2011. Altiski and Cavicchino released a paper where they did this for a particular kind of wavelet, which is the first order emission wavelet that I'll talk about in a moment. We wanted to expand on that and say what happens if you look at higher order emission wavelets, what happens if you look at different wavelets. Can we do the general calculation, can we do the calculation not for a specific wavelet, but do it generally for any wavelet, and then be able to essentially engineer some sort of response or some sort of behavior of the Casimir force using the choice of wavelet or vice versa. So what is the Casimir effect? Just to recap, I'm sure you all know. If you take two flat conducting plates in an electromagnetic field, you restrict essentially the available modes for the vacuum energy between the two plates, so that you end up with a lower energy density between the plates versus outside, and so they're pushed together. That you experience this force that pushes them inwards, proportional to 1 less to 4. Gavin pointed out the other day that if you go kayaking, it's the same thing. If you get two people in a kayak next to each other, the waves on the outside will push the two kayaks together, which makes a lot of sense. I don't know why that hadn't occurred to me before you pointed it out. Right, so just going through some definitions for a moment. We're not using the electromagnetic field, we're just using a free complex massless scalar field. There's our Hamiltonian field definitions and equal time commutation relations, so just the usual. This is before the wavelet transform. So after the wavelet transform, what we're doing is essentially applying the wavelet transform to our field operators phi hat, and then we can break that down in terms of an expression in terms of creation and annihilation operators, which are essentially the wavelet transform in momentum space of those particular operators. The commutation relations are modified, similar to the case that Dominic showed us earlier. It's a similar sort of situation. You've now got scale dependence. This is general. W can be any wavelet, so it's possible that for some particular values of things that you can get like that, you probably expect that behavior that you saw with the integer spacing for the sync wavelet to show up, for example, if you start subbing that in. So
actually, that is different, though, isn't it?
No, so that is for Shannon wavelets, that the Fourier transform of the wavelet function just gives you a whole bunch of step functions,
right.
And so the Fock ladder operators are unchanged.
Right. Because you still, okay. So the W's would be step functions or bandpass functions.
Cool. We can then express the Hamiltonian in terms of those wavelet transform creation annihilation operators, and our to actually model the Casimir effect, we're just going to impose periodic boundary conditions and then take that to infinity outside the plates, and then have a finite value within the plates. So we're interested in the difference between what we're describing as, hang on, I'm getting ahead of myself, that's on the next slide. Yeah, that's right. So we essentially just discretize the integral becomes a sum between the plates. We make those particular replacements. Everything from here down is pretty standard. All right, so what we're going to do is calculate the energy density inside the plates using our wavelet transformed operators, and we want to impose a scale cutoff. And this is the key piece for the scale cutoff. BA is our scale cutoff essentially. S is the distance between the plates, and what we're saying is that we set all of the modes below that value A to 0. Then here is our expression that rho naught is the energy density between the plates, and our cutoff function shows up and is equal to this. The difference between them is then given by this expression, and we can follow the same, roughly the same derivation that Casimir followed using the Euler-Maclaurin formula, and we obtain this expression here. Now, the couple of things to notice. One is the wavelet shows up here in this f tilde, so this is the cutoff function corresponding to the wavelet. If you're wondering what that relation is, I'll just jump back to here. It's that, so f tilde, the wavelet shows up in there. And you can, in some cases, you can go backwards, and I'll show you later on. We start with some wavelets that we're interested in and work out the cutoff function, and in other cases, we start with the cutoff function and work back to the wavelet. I don't think we've teased out exactly whether that's possible in every circumstance. Generally, I don't think. Yeah, we don't. All right, so yeah, a couple things. If you take the limit a to 0, you lose this term entirely, and you end up with the standard result. And for different boundary conditions, if you want to set, instead of using periodic boundary conditions, if you want to set them to 0 at the plates, it's more or less the same result, but with twice the distance. Cool, so detecting the scale cutoff. The Casimir force is given as the derivative with respect to the distance of the energy density as per usual, and we're going to consider the scale cutoff much smaller than the separation, and expand and see what correction terms we get for different wavelets. So that's an explicit expression for, again, general wavelets, and it involves the second derivative of the cutoff function. So firstly, we looked at emission wavelets, which are the same wavelets that Altiski and Capicini used in their paper. The emission wavelets are the derivatives of the Gaussian. In our case, because we're operating in, we want to do the wavelet in multiple dimensions, what we've done is define them in terms of a Fourier image, which means that we can be certain that they will meet the admissibility condition, and they're radially symmetric. The cutoff function is like so, and the lowest order correction is here. So this is consistent with Altiski and Capicini when you set n equal to 1. Interestingly, for the nth emission wavelet, the first n-1 corrections vanish. So that suggests, a bit like we found a similar phenomenon when we were working with discrete wavelets, but as you go to higher order wavelets and the wavelets sort of intuitively get squigglier, you can capture more and more of that fine detail for a given particular scale. So that was an interesting find. Oh, that's the first emission wavelet, I think, in 2 or 3 dimensions. I'm not sure if that would be
emission means polynomial.
No. Yes or no?
Yes. Derivatives of Gaussian.
Derivatives.
Yeah, that's how you get the Hermite.
Yes. Yeah. Cool. And almost there. So this is a figure showing the actual force itself multiplied by the scale cutoff to make it dimensionless. So we've got the standard result here, and you can see how the higher order emission wavelets, so this is first, second, and third order, so first, second, and third derivatives of Gaussian, you essentially converge from either side, getting closer to the accepted value, which is interesting. That in the discrete case, you sort of have this trade-off, because when you're working with matrices, your squigglier higher order discrete wavelets end up require more computation to calculate. So it's sort of this computation versus accuracy trade-off, where you can end up with a sparser representation in the higher order wavelets, and I think it's a similar phenomenon here. I'm just going to talk about 3 more wavelets, and then we're done. The exponential cutoff wavelet is what we get when you work backwards from setting the cutoff function to the exponential regulator that Casimir used. So you can work backwards in this case if you just set it to the exponential. You get this position of momentum description. The lowest order correction is here, and it has an opposite sign compared to the expression for the first emission wavelet. So one of the findings, I suppose, is that the corrections are not always the same sign.
So how should we understand it, in a sense? Which is
well, it's going to get weirder, Danny, when we start talking about some of the pathological wavelets, but potentially, I'm not sure. Gavin?
No, keep going, and then we'll talk.
Sorry, yeah, keep going. We'll talk at the end. And then the other thing is that for the exponential cutoff wavelet, you can get an exact expression for the force. And so here my slides become a little bit rougher. This is the cross-section of the exponential wavelet. Again, it's sort of focused, and it had focused at the origin, and it has this very small, thin negative section that goes off to 2050. I think we're running out of time. I'm going to skip this one just to say that you can use one of the things that we define is that you can use the wavelet-based regularization to come up with asymptotic expansions instead of series expansions from 0, so you can actually get behavior on both sides. This is the behavior, as the scale cutoff approaches the size of the separation of the plates. So that's works as well. That's a comparison of emission and exponential cutoff wavelets, showing the negative and positive. First order emission wavelet has the same sign correction. The exponential cutoff wavelet has the opposite sign correction. So yeah, that's not all that helpfully labeled.
Not labeled.
Well, it is labeled, just not in names.
It's labeled in maths. In properties, yeah.
Yep, done that one. All right. 2 extreme wavelets. You may remember that the general correction is in terms of derivatives of the cutoff function. So the obvious question is, what happens if you find a wavelet that has a 0 derivative? Such a wavelet may be non-analytic or have other weird properties, but maybe you could actually come up with a wavelet such that the Casimir effect is unchanged. We found a couple of weird things when we tried that. So here's a smooth step function for the as given. The Fourier image is like so. It looks like this. So Dominic talked about sinc functions which have a top hat in the momentum representation. This looks very similar to a sinc function, but it's smooth in the momentum representation.
And so that means they just decay faster in position.
They do, yeah. So this decays. So it decays super polynomially when calculating those derivatives. Another one is this one here, which is connected to I think the typical one doesn't have the 10. I think, or it might be a squared.
Curious choice.
And the 10 is there just because in order to meet the admissibility condition, it had to be that power had to be quite high. That looks like this, quite similar. And then this is both of them together. The Maya one here is the non-analytic wavelet.
So doubling of the peaks comes from what?
So What do you mean? The
On previous slide, it is yeah. So we have two peaks in momentum space.
Yes.
Okay.
Yeah, symmetric
Yeah.
and position symmetric. So this was really weird. If you start picking out pathological non-analytic wavelets, you can get corrections to the Casimir force that are oscillatory. In other words, if you've got some fixed scale dependence and you change the separation of the plates, you will find that the force becomes attractive, then repulsive, then attractive, then repulsive, then attractive, then repulsive.
Well,
No, it's always attractive. It's just that's the difference between the scale cutoff and the continuum limit.
Yeah, I checked that with Simon. Oh, well,
No, just emphasizing that the y-axis here is the difference.
The difference.
Yes, the force
Scale
itself.
cutoff.
yes, but that'd be a Simon question. He might be able to answer that in his talk. But the scale here is 10 to the minus 2. The scale for the other one is 10 to the minus 4.
No, but I mean just the y-axis is a difference. Like 0 means is exactly the continuum limit.
Yeah. Oh, sorry. Yes. Okay.
So you still feel a bumpiness in the forces, like
Potentially. Yes.
yeah,
So you could like expand your plates,
and you'll
and
feel
you'll
like
see a change of sign in the correction.
yeah, that's weird. Yeah, so it'll be easier and harder. Yeah, there'll be certain places where it's easier.
If there's a cutoff.
But there's that's right.
Cool. To conclude, wavelets are great. QFT is weird, and choosing wavelets when you are investigating QFT using wavelets is quite important. Cool. Questions?
So maybe
I'll put this one up because I think that's probably the weirdest outcome there. Yeah.
So, can there be any intuitions to what, like, properties of a wavelet? Like, let's say, you wanted to have a correction. Let's say, look at the Casimir effect. You wanted to have some sort of correction that was positive based on the cutoff.
Yep.
And is there some sort of properties of the wavelet, like of the wavelet choice, that you can look for when choosing your wavelet to get those desired effects? Like, can you almost intuit what the modification of Casimir effect would be just from the form of the wavelets, or is it more like a case by case basis? You just go through each choice.
In our case, it was the latter. We just tried some things and saw what was working. I feel like you should be able to. Like there probably is a property or something that you could find that might be something to look into.
I have this more conceptual question and maybe more physics question about this. So, if you view this as a tool of regularization, not changing the theory,
Yes.
why the results of physical observables should be different?
I don't think. Well, I think where this becomes useful is where physical observables are themselves limited in scale. So if you're looking at an observable that is essentially scale limited, if you're using a real life detector, for example, then it may be that this becomes a useful model for modeling how that detector is going to interact with the field in this situation. But otherwise, compared to if you're talking about the results in the continuum limit, then I would expect them to be the same.
Well, yeah, well, my perception of regularization is just a mathematical tool to get rid of infinities.
Yeah.
Now, you may have some regularization which affects your theory.
Yep.
So it's not exactly what you started with.
Yep.
And then you may have a different observable that you go and check that experiment or something.
Mm-hmm.
But if it's just a regularization, I still don't understand that. It doesn't matter whether the scale dependent or whatever. If it's a physical observable, it should not depend on your mathematical manipulation to get rid of it.
Yes, I think I would agree. Yeah. I think where this turns up, so when your observable doesn't match, the other thing that occurred to us is if you've got a simulation that is essentially scale limited. So if you're modeling something, if it's a condensed matter system where you have an underlying lattice, and that the forces between that lattice have some particular characteristic that can be modeled as a wavelet, for example. It may be that the non-continuum limit of the wavelet-based theory is useful, but
well, in quantum metaphysics, you might have a boundary condition which affect your spectrum. Or that could be either artifact theory or the physical result.
Yep.
Let's see what that means.
Let's keep chatting afterwards.
So let's thank Dan again.